Good morning, everyone. My name is David O'Connor. I'm the permanent observer of Iucn, the International Union for Conservation of Nature at the United Nations in New York. And I'm happy to introduce this knowledge dialogue, part of a series of knowledge dialogues organized jointly with the Permanent Mission of France to the United Nations and the Wildlife Conservation Society. This knowledge dialogue today is also a side event of the high-level political forum on sustainable development at the United Nations. It's on knowing nature, new conservation technologies and knowledge systems to support the Sustainable Development Goals and the post-2020 Global Biodiversity Framework. Just a few housekeeping notes. If you have questions, there is a Q&A function on the bottom of your webinar window. Please use that to submit your questions to panelists, to speakers, and they will either answer them in writing or in the Q&A session at the end when everyone has had his or her say. Our moderator today will be Neville, and he'll be coming on shortly. But I'm going to begin by introducing my colleague, Sonia Peña Moreno, who is the director of the International Policy Center of Iucn, based in Gland in Switzerland. So without further ado, I pass it to Sonia for some welcome remarks. Sonia.
Thank you, David. Good morning, afternoon, or evening, wherever you are. Welcome everyone to this webinar, Knowledge Dialogue side event at the IHLPF. Many thanks for joining us today. Let me open this event with a few reflections. The science is clear that our window of opportunity to effectively tackle the interconnected crisis of climate and biodiversity loss is narrowing by the minute. Yet, the international community has multilateral treaties designed to address both of these crises. The Convention on Biological Diversity being one of them, and the UN Framework Convention on Climate Change, for instance, another one. In Paris in 2015, right after the adoption of by the world's leaders of the 2030 Agenda for Sustainable Development and the Sustainable Development Goals, parties to the UNFCCC, so the Climate Convention, agreed to work to limit the global mean temperature rise between 1.5 and 2 degrees Celsius above the pre-industrial levels. This temperature target was informed by climate science, as reflected in the IPCC's, the Intergovernmental Panel on Climate Change, successive reports. The parties to the Convention on Biological Diversity are at the moment negotiating a treaty, a new agreement to tackle the loss of biodiversity. This new biodiversity agreement will be framing new targets and goals to address and halt the loss of biodiversity. They will meet in the Conference of the Parties at the end of the year, now set to be taking place in Montreal in December. To achieve those goals and targets that are being designed and framed under the Convention on Biological Diversity, science has to be addressed or has to inform the discussion of those appropriate goals and targets. For instance, through the advice and guidance that is provided through the Intergovernmental Platform on Biodiversity and Ecosystem Services, the IBVES. Just as science is critical to guiding policy to keep humanity within ecological limits, so too are technologies that are critical to guiding efforts to achieve any science-based goals and targets to which the international community adheres to. Climate action calls for the adoption of a range of technologies. Some are already well tried and tested, like renewable power. Others are still to be perfected, like engineered systems of carbon capture and storage. Action to tackle the biodiversity crisis also depends importantly on new technologies, as well as traditional systems of knowledge, increasingly codified and integrated with modern information and communication systems. Earth observation satellites are an early example of such technologies. And increasingly, nature conservation is making use of these advances, including on artificial intelligence, genetics, and a variety of other technological innovations that you will hear about here today. We must not forget, though, that nature itself consists of a complex set of technologies that have been adapted through eons of time to optimize species survival and ecosystem health. As we move ahead to tackle the climate crisis, the biodiversity crisis, and other pollution, etc., we should take advantage of the solutions that are offered by nature, including by using technologies, nature and nature-based solutions. These solutions can protect us from disasters, protect our food and water supplies, support adaptation and mitigation efforts, keep us safe, provide goods and services to human well-being and economic development. So let's hear about all these technologies from our experts here today on behalf of IUCN, WCS, and the Permanent Mission of France to the UN. I welcome you all, and let's hear from the experts.
Thank you very much, Sonia, for that those welcome remarks. And now we're pleased to have Monsieur Denis Duclos, the head of the International Cooperation Department of the National Museum of Natural History of the Republic of France, offering some introductory remarks. Denis, it's yours. You have to unmute. Unmute your microphone, please.
Can you hear me right now? Can you hear me?
Yes, yes, we can hear you now.
Okay, sorry for that. Thank you very much, David, and thank you very much, Sonia, for your introduction. And before starting, hello, everyone. I would like to thank the organizers for their invitation. It is a pleasure and an honor to take part in the discussion set up by the permanent representation of France to the UN, the IUCN, and the Wildlife Conservation Society. Ecosystem degradation and biodiversity loss pose huge challenges for our future on this planet. Technology plays a prominent role when it comes to better understand biodiversity and foster its preservation, whether it is marine or terrestrial. The exploration of deep sea areas, for instance, requires high technologies such as the French Nautic submarine, the remotely controlled Victor 6000 robot capable of working to a depth of 6,000 meters, shedding light upon the existing biodiversity in these areas and consequently raising the question of its conservation at a time when the exploitation of deep sea is considered. Using high-resolution pictures from satellites is also common in order to increase knowledge regarding the distribution of phytoplankton on the surface of the sea, for instance, or the repartition of migration species in the current context of global changes. Barcoding technologies or high technology platforms enable scientists to deepen their investigations and to push forward the frontiers of awareness. Thousands of new microscopic organisms have been discovered thanks to metagenomic technology, opening large, new, promising scopes for new discoveries. We could also mention the digital twin ocean, which is a consistent, high-resolution, multidimensional, and near real-time virtual representation of the ocean, combining ocean observations, artificial intelligence, advanced modeling operation on high-performance computers, and accessible to all, let alone mentioning big data. Not only is technology crucial to improve knowledge upon biodiversity and habitats, which is the prerequisite to preserve them since we can only protect what we're aware of, but it is also a key actor to raise people's commitment to respect them. Digitization is a major tool when it comes to provide a large access to information and to employ a large audience in upgrading the species inventories and their habitats, for instance. The museum has had to carry out these inventories for decades, according to the constitutional decree which regulates its activities. To raise the interest of the largest audience as possible, the museum has implemented a wide array of so-called citizen science programs mainly based upon digitization, where everybody can take part in via the active collection of biodiversity data in their immediate environment while respecting a strict scientific protocol. Resorting to technology is also significant and is also a useful tool regarding training professionals committed to the preservation of biodiversity, habitats, and environment. To name a few, the museum has set up an online curriculum tailored for professionals centered to the management of botanical garden. It has also organized an online workshop in environmental diplomacy for the attention of the Caribbean islands for them to enlarge their skills in the field of high-level multilateral negotiation. Let alone the CITES, which intends to resort to technology to issue standardized and digitized permits of exports and imports. By doing so, CITES expects to be more effective in the fight against illegal trafficking. Nonetheless, the use of technologies, especially high technologies, imply, first, to cooperate at a national, regional, and international level. The steadily rising cost of technologies compel parties to work together in order to soften their financial burden. France and the European Union have been implementing the program called DISCO, whose aim is to set up a distributed system of scientific collections, harboring a massive amount of specimens, implying 5,000 scientists, more than 170 institutions based in 23 countries in one single European collection. Other examples of multi-stakeholders cooperation set up with a view to reducing national funding can be found easily. Second, to implement capacity building programs. When it comes to use technologies, mastering them is essential. This can only be completed by sessions of skills enrichment via training. In other words, capacity training programs, which are mostly based upon international cooperation, play a central role. Each party to the Convention on Biological Diversity has to implement its own clearinghouse mechanism, i.e. a website aimed at presenting the actions and measures taken by the parties to protect their own biodiversity. In this perspective, the museum and its partners set up a capacity building program for the French-speaking African countries dedicated to the use of the content management system developed by the Convention to upgrade their national CHM. The ongoing negotiation under the Convention on Biological Diversity endeavor to create a post-2020 global biodiversity framework to protect it in a more efficient way than the previous Aichi target did. It goes without saying that technologies and new technologies are to support this new framework, especially for its implementation. Should it be eventually subawarded, the target of 30% of protected lands and seas by 2030, supported by the High Ambition Coalition for Nature and People, co-chaired by France and Costa Rica, and which now counts 102 members, is a typical indicator which needs resorting to technology. Together with a strong political involvement, the management plan of a protected area needs technology in order to be fulfilled, assessed, and, if necessary, readjusted. But we have to make sure at the same time that technology has no boomerang effect. In other words, that it will not be harmful for biodiversity. Artificial intelligence, digitization are undoubtedly useful, but their use must be assessed and not taken for granted. Nor should we consider that technology is or will be the answer to biodiversity loss, nor can technology replace it. These are questions of consistency that the museum and its partners are paying great attention at via, among others, the establishment of an internal reflection group on ethics dealing with these important topics. I'm very glad to listen to our panelists, and I would like to thank you again for your attention.
I'd like to thank Denis for that very interesting presentation. And now I'm happy to pass it on to Neville Ash, who I hope is still with us. I don't see him on the screen.
I'm here, David, I'm here.
Oh, there you are. Okay, good. So Neville, you'll take over from here. Thanks very much.
Great. Thank you so much, David. Thank you, Sonia, and thank you, Denis. Superb introduction to our session today. And we've heard from Sonia about the urgency of addressing the biodiversity crisis, the need to move quickly to ensure we make progress towards, yes, the SDGs, but also the post-2020 global biodiversity framework. And we heard from Denis about the exciting opportunities that conservation technologies provide. and some of the caveats and cautions we need to think about as we take forward conservation technologies. And of course, this is all going to depend on bringing together the conservation community and the technology community to work together to realise the opportunities there for conservation benefit from available technologies, which are rapidly emerging and developing. Almost every week there's a new development, new announcement. We're going to hear lots about that today. Let's start though with our session from hearing from Talia, speaker, who works with Wild Labs, the research lead at Wild Labs with WWF. And Wild Labs is incredibly important as a mechanism for bringing together the conservation and practitioner community and technology practitioners as well. So very keen to hear from Talia an overview of the issues we're going to then focus in on a bit more detail with some examples of key technologies as we go into our panel following from this. So with that, Talia, over to you.
Hi, everyone. Thank you so much, Neville, for that introduction. And thanks all for having me here today. I'm really happy to be here, as Neville mentioned, to provide a brief introduction to the state of the field of conservation technology and kind of set the scene for our other speakers in discussion today. So when people talk about technology supporting the SDGs and other global goals, as mentioned, I find that it's often focused on advancements in other industries like healthcare, agriculture, or energy. And so the first main message that I want to highlight today is that technology is already playing a huge role in biodiversity conservation in diverse ecosystems all over the world. It's enabling more effective data collection, targeted monitoring, and enhanced management and decision-making. The second point that I want to make sure we cover today, and what we're mainly here to discuss, I think, is that despite all of these amazing efforts, there's still huge untapped potential remaining for using technology to advance progress and also monitor progress towards global conservation goals. So while there's a lot of inspiring work being done, we're not doing nearly enough to keep pace with the current challenges at this point, and we need support to get there. And on that note, I hope that by the end of this event, everyone here will recognize that you all have a role to play from whatever position or sector you're coming from in ensuring that these efforts get the support they need to actually harness this potential and help us make progress towards these goals. So for a bit of context on my work in this space and why I'm here giving this introduction, I lead the research program at Wild Labs, which was launched in 2015 as a partnership between 5 leading conservation NGOs listed at the bottom of the screen here. And it was launched with a mission to catalyze collaboration to accelerate the development and scaling of technology solutions for conservation impact. It was really created as a space for people working in conservation and technology to come together and find collaborators, source information, share ideas, and find better ways to approach our conservation challenges with the support of tech. And over time, it's grown to an active community of over 6,000 members. I see some of our members are here today, which I'm excited about. And it's really become the go-to place online for all things conservation tech and is expanding beyond kind of just that connection building that we were initially launched to do. So just to give you a really brief glimpse into what's already out there in the conservation tech community, this is a screenshot from the latest photo challenge that Wild Labs runs every year on Twitter, where we put a call out to the community and ask them to share images and videos of them using technology in their conservation work and explaining what they're doing and how it's empowering better conservation. And we asked them to do this using the Tech for Wildlife hashtag, which is searchable. So I would recommend going and checking it out after this session if you can. So over 6 years, we've seen over 6,000 tweets around this hashtag with more than 1,000 photos and videos posted, showcasing a super wide range of applications. And just a few examples are biologging tags collecting movement data and video on orcas in Norway, open source sensors monitoring penguin colonies in Antarctica, drones studying orangutan nesting habitats in Indonesia, individual brown bears identified with the power of AI in Alaska, and much, much more, as you can see. So along with our photo challenge, each year at Wild Labs, we survey our global community to understand what they're doing, find out what challenges they're facing, and ask what support they need from us and our partners. And over the years, noticing that input from this community was consistently describing these kind of big picture systemic constraints that were spanning technologies, ecosystems, and landscapes, we decided to formalize the process last year to deliver a global community-sourced assessment of the state of the field, the state of conservation technology. And we published this in the Journal of Conservation Biology in December. In addition to the survey, we also ran focus groups with around 50 leading experts across some of the most widely used technology applications in conservation to kind of get a greater depth of understanding and help triangulate findings from the survey. And part of the motivation for this was that while there have been some really valuable review papers and assessments around specific technologies in recent years, to our knowledge, this was the first attempt to actually formally capture the perspectives and needs of the conservation tech community, according to them, according to the people who are using and developing these tools. And the hope was really to be able to amplify a united voice to drive progress towards more effective solutions, both in our own work, but also by sharing the findings with global stakeholders like all of you here today. So I'm going to go over just some of the really high level kind of takeaways from this research. The first, this is just basically showing what tools are being most widely used in the field. I won't go into a ton of detail on these, but basically this graph shows that technologies are, basically there's a wide range of technologies being used in the field. Some of them are more highly adopted and widely adopted than others, including camera traps, GIS and remote sensing, and machine learning and computer vision, which are both artificial intelligence tools. You can see those are the most widely used right now of our survey respondents. And then other tools like protected area management systems and eDNA, which is environmental DNA and genomics, which I think we'll hear more about later. These kind of appear to be less widely adopted, although we do know that specific user communities really rely on these tools heavily. So in terms of current performance, we were interested in understanding first how are tools performing right now, what's working well and what's not, and then how do people expect that these are going to influence the field of conservation in the future. And we saw that respondent ratings currently show that GIS and remote sensing, drones, and mobile apps are seen as the current high performers of these technologies. And these are all tools that have had some time to become kind of somewhat established in conservation settings, which is kind of interesting. And then there are other tools, you'll notice lower down on this list, tools like machine learning and computer vision, eDNA and genomics, and network sensors are all pretty new to the field of conservation, and so are kind of probably going through these growing pains. But looking at their trajectories, these are the ones that people are really expecting to significantly advance the field in coming years and are seeing as having the highest untapped potential right now. Some other tools like protected area management systems and drones are seen as kind of performing well right now, but having room to grow. While others like camera traps may be seen as having already been around long enough to have kind of largely contributed their quote unquote game-changing advancements. So then we wanted to move beyond specific technology applications and ask about the greatest challenges facing the field of conservation technology as a whole. And when we asked about this, we saw that competition for limited funding, duplication of efforts, and technology adoption and capacity building were seen as the most pressing concerns. And these, I think, kind of reflect what we heard from Denis earlier in terms of those needs. And they were also really strongly reinforced throughout both the rest of the survey questions and the expert focus groups. So for example, when we asked about the different constraints that technology users and developers might differently face, end users reported that their most pressing constraints were costs and technical barriers, and technology developers reported struggling most with financing and coordination. So again, this kind of really reinforces that sustainable funding sources, coordination of efforts, and building technical capacity in key conservation communities really are the primary concerns and needs. Then one other point that what I think was really important in our research was that when we went into these more in-depth kind of constraints analyses and looked across groups, our our data revealed that a range of financial and technical barriers may be disproportionately affecting women and individuals in countries with developing economies. And these dynamics showed up in the form of signs of inequality and financial accessibility to end users, with users in countries with developing economies being significantly more likely to struggle with the costs, both upfront and maintenance costs of conservation tech. We also saw a potential gender divide in perceived technical skills, with female users being significantly more likely to report struggling with technical skills than male respondents. And lastly, we saw signs of inequality in sustained financial support for developers, with both female tech developers and those in lower income countries being more likely to report struggling than their counterparts with securing longer term funding for work, so to support their work throughout the technology development cycle. And these trends really highlight the need, we think, to evaluate and address potential exclusion of critical conservation stakeholders who we know are fundamental to our efforts, making sure that the broader trends that these reflect that we know exist in both the conservation and technology sectors aren't undermining efforts in this space. So despite all these challenges, we were also happy to see that the community has remarkable hope for the future of conservation technology. And when we asked about what made them optimistic, the primary reasons were the increasing accessibility of tools. So talking about both cost and usability, the rate at which the discipline is evolving. As mentioned, I think there are new developments in the field and new tools coming up every week, it seems like, and more effective tools as well. And then finally, the collaborative culture of the field, which we're also always so impressed by and working to facilitate as well. So along with this optimism, the community also pretty clearly defined an ideal vision for the future of the field of conservation tech. And they described a vision in which collaboration trumps competition, solutions are open, accessible, and interoperable, user-friendly data processing and analysis tools empower the rapid translation of data insights to conservation action, and local and indigenous communities around the world are empowered to engage in building and using the technologies that really best suit their needs as stewards of their lands. So looking ahead, I think defining this collective vision was a really important step. And now that we have it, and we have this kind of critical baseline data that we can use to measure progress moving forward, our team at Wild Labs and our partners are really getting to work starting to bridge the gap between them, and are hoping that others will help us do that as well. So with these high potential tools like AI and genomics and network sensors, we know they're already revolutionizing a lot of the world's largest business sectors. And this research definitely does reinforce the huge opportunity to invest in harnessing their potential for conservation. But it's also clear that advancing the field and really harnessing the potential of conservation tech is going to require a lot more than just investing in promising tools. So according to our input from our expert focus group discussions, overcoming these challenges to actually achieve scalable impact is going to require much more dramatic shifts in the way we're approaching our work, away from this kind of patchwork landscape of projects that are competing for limited resources, and much more towards the direction of an internationally coordinated field and kind of organizational ecosystem with innovative funding mechanisms to back it. And just a few of the key elements mentioned by focus groups that they believed could really advance progress on this front were targeted investment in infrastructure to support the collaboration that clearly there's so much willingness to engage in. So for example, like open community curated data repositories. Also resourcing and defining industry standards, ideally building on existing standards elsewhere that we can really clearly adopt and use in conservation settings. And finally, to improve coordination and scaling up efforts. This idea of basically a national lab model or international lab model for conservation came up a lot as a potentially critical kind of coordinating body, working with existing bodies, obviously. So just a couple of notes on what Wild Labs is doing in this space to try to address some of these gaps through our own programs. We are, as I mentioned at the beginning, definitely evolving alongside the needs of our community. So building on our core platform that we were created to host, we're also now running projects that bring experts together from across sectors through virtual exchange series and virtual events. We're also running a pretty large editorial program now, kind of trying to feature and bring to light and bring to the public the amazing work that's going on in our community. We're synthesizing insights from our diverse global community through research like this state of conservation tech work, and working with funders like the Moore Foundation to try to kind of harness some of that collective expertise to make sure that that's going towards informing investment and engagement opportunities. And increasingly, we're also working to bridge the gap between the conservation and technology sectors by doing more matchmaking and bringing in skills and resources in the form of technology fellowships, AI office hours, and other capacity building programs. And then lastly, we're also growing to establish more regional communities to support more diverse engagement in the field in light of those findings. And we're starting this with a Women in Conservation Tech program in East Africa that we just launched, and are working to build better infrastructure as well as part of our platform to better help basically document and engage with existing solutions in the field. So with that, I think the last message I want to share is that while there's a lot of inspiring progress happening in this space, the reality is that, as I said, capacity is still limited, and especially with all of these systemic barriers to engagement, we just aren't progressing quickly enough to keep up with escalating challenges or meet these critical goals. So we need all of you in whatever way you can engage. And I really think there is a role for everyone, whether that's through working with or supporting Wild Labs and the members of our community, through bringing more sustainable approaches to technology into policy and funding conversations you're having, or even just approaching your work with more openness to collaborative innovation and the role it could play in a better future for our planet and society. Please feel free to reach out with any questions, and I look forward to more discussion. Thank you so much.
Wonderful, Talia. Thank you so much indeed. Brilliant overview of some of the issues here and some of the progress that's been made. And really interesting graphics there around the transition and importance and recognition of the importance of different technologies for conservation impact. And of course, some of these technologies are very old. We've had camera trapping for over 100 years now, not applied at scale, but in terms of a technology which can be used. eDNA for the last 40 years or so, AI since the early 1950s, not all applied to conservation, of course, in that time. But we should recognize as we go through these conversations today that many of these technologies have had a relatively long history of development, and we're bringing them now to conservation, the conservation game, which is a super exciting period of development and time to be in. Let's go on to our panelists then to go into a bit more detail around some of these particular technologies. I'm going to encourage everyone who's participating today, continue to introduce yourself in the chat box there, but please put your questions into the Q&A box, which you'll find at the bottom of your Zoom screen as well. So as we're going along, a question comes to mind. It might be something you've heard from Talia. It might be in relation to anything you're about to hear from our panelists. Do drop those questions into the Q&A box, and then we'll answer those as we go along, and we may have time to come back and have some more discussion in relation to them at the end. But I'm delighted that we are joined today by 5 panelists who go into a little bit more detail on some of these key technologies which are rapidly developing and being applied for conservation. And so let's start our work going to Coral Reefs. We're going to hear from Emily Darling, who's the Director of Coral Reef Conservation at the Wildlife Conservation Society, around technologies and coral reef monitoring and management. So Emily, over to you.
Thank you so much. Can you hear me and see my screen?
Perfect. You both. Yep.
Wonderful. Well, thank you very much. It's an honor to be here. My name is Emily Darling, and I'm the Director of Coral Reef Conservation at the Wildlife Conservation Society. And the technology that I'm really excited to tell you about today is a collaboration between WCS, WWF, and SparkGeo. So as we all know, achieving this intersection of crises is so critical to our times. And I really believe that coral reefs can be, a critical ecosystem in doing that, specifically that interrelationship between the biodiversity and climate targets and the Sustainable Development Goals. And of course, this is because we know that coral reefs are among the most biodiverse ecosystems on our planet. They support 500 million people with food security, livelihoods, culture, and coastal protection. And of course, they're on the front lines of climate change. So we must do what it takes to save coral reefs. To this end, the International Coral Reef Initiative includes more than 45 countries that are custodians of over 75% of the world's coral reefs. To inform post-2020 negotiations, ICRI has adopted a consensus recommendation of global coral reef indicators, and you can see those here. What I'd like to highlight is that the majority of these indicators require this: people underwater. Having eyes on the reef like this is some of the only ways that we can actually measure these key indicators. Satellites and drones can map habitat or look across vast scales of coral reefs, but they can't see through the water. And so engaging a global community of underwater monitoring scientists through technology is critical to bringing to light these key indicators. Now, this is particularly important for key reports, such as one you see here and may be familiar with, the 2020 Global Status of Coral Reefs. And as the authors of this report will tell you, and I'm one of them, these reports take too long because we cannot bring together this data at scale. Before I move on, I'd just like to highlight that our technology underwater is extremely low tech. You can see rubber bands, pencils, transect lines here in these photos. And where we really go tech is when we come up to the cloud. And that's what I'll talk about today. So as we know, technology has to accelerate how we measure data-driven progress towards these critical global targets. And MERMAID is an example of that. MERMAID stands for a Marine Ecological Research Management Aid. It is a free, cloud-native, open-source platform for coral reef data. It is used in 27 countries, contains data from over 35,000 underwater transects, more than 3,600 sites, has 33 years of surveys, and more than 1,000 global users from 77 organizations. I simply share these numbers to show that this tool is being used, and it is a game changer in coral reef data and conservation. In particular, this is a human-powered platform from those people that you saw underwater in those earlier photos, and it is transforming how we collect data from underwater surveys across coral reef fish, which is obviously critical for fisheries and livelihoods, into the coral and benthic architecture, the backbone of a coral reef, and then into bleaching and the impacts of climate change. And one of our missions in particular is to also leverage global science data sets for rapid analysis and reporting for users at all scales. So to give you a sense of what MERMAID does, the problem we're trying to solve is very, very simple. It's data in and clean data out. And I'd like to highlight that anyone can use MERMAID to export and share those key indicators that we've been speaking about. Here's an example of a user exporting the data that they've entered into entered into MERMAID, and now having a clean, standardized, output that they can use, collaborate, and share on. MERMAID is also powered by API. So it's built fully in the web as a cloud-native dashboard, or a cloud-native platform. And this means that we can have cloud-powered dashboards. What this means is that users can visualize their data to track the status and trends. So here you can see our dashboard. We can dive into Glover's Atoll in Belize, a critical managed area in this region. We can see what are the status of coral reefs, and we can look at how that's changing over time in terms of the effectiveness or benefits of management. Now, in terms of leveraging global science, cloud-native platforms are critical because they can bring together those field observations with other global data layers. What I'm showing you here is an example of a recently published global map of the top threats and cumulative threats of human pressures to coral reefs. Normally, these data would be in a beautiful Esri platform somewhere, difficult to download or leverage. But with MERMAID, we've connected these two platforms through the API and now download each of these observations with users' field data. So connecting underwater observations to large-scale data sets is also something that these field powered and field practical platforms can do. And lastly, I think that call to have innovative collaboration, to be connected and collaborative is so crucial. You've likely heard of the Allen Coral Atlas, and I just wanted to highlight that we work closely with them and share data to improve both platforms. And we do this because it delivers field and satellite data on SDG indicators and on the post-2020 indicators to decision makers. You can see here in this graphic that by having satellites in the sky and people underwater, we're able to deliver a full suite of indicators to decision makers. Now, as I wrap up, I wanted to give you an example of how this is actually being used in the real world. In Fiji, in the photo you see here, Indigenous peoples are rights holders and resource stewards. This is Nauo village. After a devastating cyclone in 2016, this community lost access to fresh water and crops. With hunger looming, the chiefs decided to open up their local tambus, or local no-take managed areas on a reef, so that community members could fish and eat. The community survived. Several years later, the chiefs wanted to know, should they close their tambus again to rebuild their fish populations so that they could be prepared for the next cyclone? To help answer this question, WCS scientists visited the village and surveyed coral reefs with local community members. And with Mermaid, we analyzed the data and presented the results back that night to communities around the Kaba Bowl. We found that the tambu was below sustainable thresholds of reef fish biomass, and it could be closed to help rebuild that biomass in anticipation of, unfortunately, future disasters. I want to highlight this story because it's an example of how the adaptive management cycle that we've heard about happened in one day because of a field-ready and practical technology. Instead of taking months or years for the data to go back to SUVA, to be cleaned and processed and analyzed, to then come back to the community, and the opportunity to build that trust and build those relationships has to start over again. But with Mermaid, this was able to happen all in the same day. Now, I think Mermaid's pretty great, but don't take my word for it. And just very briefly, let's hear from a few of our key partners.
Mermaid is my go-to platform to get information on the health of Fiji's reefs, to share it with our communities and government partners. The more we use it and WCS and partners add data to it, the greater its value for Fiji as a country.
And from Francis Staub, the global coordinator of ICRI, who notes that Mermaid will be a critical tool in helping governments implement and measure progress towards meeting the ambitious goals and targets of the Global Biodiversity Framework. So wrapping up, in summary, field-ready cloud-native platforms can help engage stakeholders in rapidly measuring data-driven progress towards key global targets. I think Mermaid is an example of how an emerging technology is accelerate how scientists and stakeholders together collect, analyze, and share coral reef data rapidly. And of course, this near real-time field data is critical for decisions across all scales, from local to national, and will greatly improve how we make decisions to boost ecosystem management and ultimately climate resilience. Thank you very much, and I look forward to hearing from the other panelists and bringing you face-to-face with coral reef data and conservation technology. Thank you.
Brilliant. Thank you so much, Emily. Fantastic example of how some superb technology is being brought to bear at very local community scales there in Fiji, and some great testaments to the value of doing that. So that's fabulous. Thank you very much indeed. A reminder, if you want to ask a question, please put it in the Q&A box, but do keep your chats coming. Let us know where you're listening in from. Let us know about the work you're doing, the platforms you're developing, the exciting technologies you're using around the world as well. Put that in the chat box. Questions, put in the Q&A box. And let's move on then to our next panelist. So we're going to hear from Hal Holmes. He's the Chief Engineer at Conservation X Labs, and he's going to tell us a bit more about this amazing technology rising rapidly up the scale that Talia showed us earlier of use, and that's eDNA. So Hal, over to you.
All right, yeah, thank you for the introduction, and thank you to David and the organizers for the opportunity to present today. So at Conservation X Labs, our mission is to end human-induced extinctions, and we're approaching it through technology and innovation. An example of this is a project that my team has been working on for the last 5 years, where we're taking genetic testing, DNA and RNA testing, and then moving it out of the lab and to the front lines of conservation. So genetics is really useful to help you find things that you can't see, or things that are really hard to identify. And so typically when you say environmental DNA or eDNA, you're referring to DNA that's in water. And so this is from skin cells or excrement that's sloughed off from fish that are in the water. But you can also get DNA from air and from soil. So air, you have pollen, dust, or other genetic material that is coming in through attached to particles or droplets. And then in soil, there's, whoops, sorry, my slides are taking off on me. There are microbes, or there are, again, like things that are like sloughed off from animals in the soil. And you can get the DNA by running like the air or the water through a filter, pumping it through a filter. And then soil, you can take a sample of the soil, just taking a punch of it, or you can actually run water across the soil, and then you can collect that water and then filter that down like you would for eDNA. And so it's really helpful for finding elusive species. And it can tell you like what species are here, or if you're something you can't see if you're looking for a disease or a pathogen in that environment. But you can also get DNA directly from specimens. This is really critical for illegal wildlife trafficking, where many wildlife products are already processed. It's in a powder, it's a carving, or it's furniture, where you can't tell what species it came from. But the DNA doesn't change, and so you can take a sample, you can take a swab or a tissue sample, put it in a tube, and then you can look at the DNA and actually see what species it came from, or even where it came from. And similarly, if there is a wet market, or if there are live animals, you can test them for a potential disease or a pathogen that you don't want. You don't want at the market, or you don't want getting into a sensitive area. And almost entirely all of the genetic analysis is done in centralized, like highly equipped labs, like what we see here. And the sample, whether that's like that filter, the soil sample, or the tissue specimen, will come into a lab where there's a highly trained, like a laboratory scientist or a clinical lab scientist that will process that sample, which can be really tough for some samples to extract that DNA. And then they'll run PCR or sequencing, where you're looking for what are called like DNA barcodes. So it's a certain indicator that's specific to a species or to a target. Or with next generation sequencing, like this Illumina instrument you see here, you can do broadband sequencing. So you kind of look at like whatever's present there. So for a water sample, you could really see like what are all the species that have been recently in this in this area. And so it's really powerful, and it can be really cool. And, these labs are impressive. The methods, they work really well. They got us through the pandemic. But these labs, they are centralized. They're far and few in between. And in some areas, it's a long ways away from where biodiversity is and where the threats to biodiversity are. And so in some regions, like the closest one is the closest lab is even in another country. So those who are familiar with the Nagoya Protocol from the Convention of Biodiversity, transporting a wildlife sample across international borders has its own sets of challenges. And because the labs, you have this highly trained person, capacity becomes limited. A year, 2 years ago, you could take 2 weeks or more to get your COVID test back. That's a human diagnostic. In wildlife forensics, it's not as high of a priority, unfortunately. And so these turnaround times can become pretty long, and that can be really problematic when you have a decision you have to make quickly in enforcement, or in adjusting a management cycle to a problem that you have to respond to. And so what our work has been focusing on is what we found is many problems, and the applications that can be served really best is you don't necessarily need everything that you can do in a lab. Like, it's a very specific question that needs to be answered like on site, and as soon as possible. It's is there Chinook salmon here? Yes or no. Is this beef? Yes or no. And this testing needs to be done by the people who are out there. It's by a park ranger, by an enforcement official. The sequencing in genomics is awesome, and that it's amazing for ecological research, and we want to see that grow too. But what we've been working on is enable that testing in the field. So it's a battery powered, it's a portable testing system that can do everything that a PCR test can do. But we've implemented it with these easy to use test kits that are designed, for that, customs official, for that park ranger, it's, for non-scientists. And some of the challenges that we've had to overcome in the system, we've had to make, the test kits, make them shelf stable. So you don't need a refrigerator, you don't need a cold chain or a cooler to take them out to the field. Had to make the instrument, easy to use, but also durable. So it can withstand dust, can withstand water. And then also making things really interchangeable. So we use these interchangeable test kits. So you can use the same instrument, but then customize for that workflow and for that customize a cartridge for that specific target that you're trying to find or that question you're trying to answer. And so we've designed this, and we make the workflows with the kits so that an enforcement official, again, an inspector or any agent of conservation that's out in the field can actually implement and run this test. And so zooming out, what we're, applications that we're excited to be working in, and ones that we're just excited about to see, genetics take on in conservation, really containing invasive species, whether you're monitoring an ecosystem, if, a sensitive ecosystem, to prevent an invasive from getting into it, or, following up on eradication efforts, or in environmental risk assessments, if there's an area that's a candidate for development, figuring out if there is an endangered or protected species there. Those go towards our SDGs of 14 and 15. But you can also screen for pathogens, both in that water source itself or in the wastewater. And that also aligns with the SDGs 3, that good health and well-being, and 6 are clean water and sanitation. And I talked a lot about illegal trafficking as well, but also testing for zoonotic disease, both in wildlife and in livestock. That covers health and wildlife. And so you can prevent really major herd losses, which also goes towards food security. Testing can also be done in crops, so you can actually identify if there's a fungal pathogen that gets into a plant. It's usually weeks before first symptoms occur, and so then this can be used, again, to prevent food waste and to ensure food security. And contamination that can come from bacteria or other pathogens getting into food. You can also find from rapid genetic testing. And so hopefully I haven't gone too far over in my time. And a couple of questions I just wanted to leave for the panelists and the audience. I'd love to hear questions about where genetics or really on-site rapid DNA testing could address problems that you're all working on and that you're all facing, and then questions of how we can integrate our technologies together. The video is here another team at CXL that has an AI algorithm that can be deployed like on the edge and camera traps to actually rank and detect limping or lameness of animals, and to me this is like a really good indicator that we could test those animals for a disease. I'm really curious other areas where we could integrate different management programs. So big thank you to my team and to our funders, and to all of you for being in attendance today, and I'd love to hear from you, so please reach out and contact me at hal@conservationxlabs.org.
Brilliant, Hal. Thank you so much indeed. Again, demonstrating very clearly the wide range of applications there for eDNA technologies as well. And I'm glad you explained the cow images on the final slide. I was starting to wonder where we were going with that. So a fabulous application there of technology. So thank you very much. And you've raised some important questions there, which I'm going to encourage panelists to pick up on as we continue our sessions, but also we'll have time to come back to at the end to pick up on key questions. Likewise, let me continue to encourage any of you participating today, with 123 participants online, to drop your questions into the Q&A box. Thank you, Emily and others who've been already picking up on some of those questions and giving you some responses to those. So let's go to our next panelist then. We're going to hear from Jon Miller, who's the Chief Technology Officer at Dendra Systems, and we're going to hear about ecosystem restoration using drones. Jon.
Thank you. I appreciate the introduction. On behalf of my board of directors, including Tom Chi of @One Ventures and Nicole Connor of Airbus Ventures, alongside our co-founders Susan Graham and Matthew Ritchie of Dendra Systems, I want to take a minute to be grateful for IUCN, WCS, UICN, and all the French partners who will be thankful that I didn't try to pronounce their full names. Their leadership and all those who put this Knowing Nature event together. You guys are just simply terrific. Building community, investing in courageous shared vision while exploring the hard-earned experience and what it takes to make the knowing of nature happen matters. So thank you for that.
John, just to check, we're seeing your notes page's next slide view.
So thank you for
there's a quick button to
me.
press to make it presentation mode. That's fantastic, but I don't want to lose what we have. So if there's a quick way to fill the screen, that's fantastic.
Sorry, I'm not sure. I seem to be having an issue then.
Otherwise, we'll make it work. And maybe we can find a way to get some PDFs of the presentations up online for people to come back to afterwards, if that works for the presenters.
Is that any better?
That's perfect. You're good to go.
I picked the wrong small box. Thank you for that. Sorry about that. So basically, let me get back to it. So we look forward to collaborating with everyone on the call and in the audience. If you guys have ideas, big ideas and little ideas alike to work on together. So I want to welcome everybody to my talk on environmental technology for ecosystem restoration at scale. I'm Jon Miller again. I'm the CTO for Dendra Systems. We're a global company. So the Earth is still out of balance. Despite all the commitments made in the last decade, the rate of land degradation is higher than the rate of land restoration. So it causes a net decrease in biodiversity in our natural ecosystems. How much? Well, it's 12 million hectares of land are degraded each year. That's about 23 hectares per minute. So our current rate of species extinction is more than 10 times higher than it's been in the last 10 million years in our understanding. Dendra Systems empowers humanity to restore the balance of our natural world by providing the data and technology needed to scale ecosystem restoration. We combine ecology operations and AI in a single platform to capture and analyze huge detailed ecological data sets from remote sensors mounted to satellites, planes, and drones. This empowers customers with new insights to direct restoration work, to monitor ecosystem health, and to deliver reliable, highly precise assessments of their carbon and biodiversity progress. Our aerial surveys can capture ultra-high resolution data, so environmental managers see the land hundreds of times more accurately than conventional satellite or aerial imagery alone. We can visualize, localize, and quantify entire ecosystems down to the species level. That means single plants. We can see the difference between one native creeping vine and another invasive vine by stem and leaf patterns. So, sometimes they're like this, sometimes they're lined up, right? As if you're standing right above them. We account for every leaf and every blade of grass in that data at the entire ecosystem scale. Environmental managers now can consolidate all restoration plans. They can optimize decisions, generating outcomes, monitor progress, and enjoy access-controlled, transparent ESG reporting across all stakeholders from a single place. That single place is the Dendra Comprehensive Management Platform. To grow biodiverse ecosystems that sequester atmospheric carbon, we swarm drones to deliver seeding over diverse terrains, 11 times faster and 3 times cheaper than traditional remediation methods. I want to share that many people get excited on my engineering team. I was talking to one of our female engineers because I know having females that are in leadership positions, like our female-led company as well, is important in this endeavor. But they were getting excited, literally jumping up and down on the concrete floor as they were learning about new seeds that they had to engineer solutions for spreading. From coastal seed mixes for blue carbon, that's great fun for us. And it's completely different than the challenges of arid seed mixes to combat desertification, or the arboreal seed mixes that we used in koala corridors that we've grown with WWF in partnership in Australia. So think about it. Historical boots on the ground ecology methods for surveying consume time. They're manual. They're filled with health and safety challenges. They're constrained. They're effectively constraining the scale of work and not able to go across difficult terrains sometimes. These traditional limits can limit the ambition of project managers who are looking to scale projects with their tiny funds. Dendra solutions disrupt these traditions. We see and know nature better. By quantifying biodiversity at the species level, we're able to see and analyze habitats and fauna within that data over larger territories. We identify risks from erosion and invasive species to ensure managers maintain premium biodiverse carbon ecosystem assets. We deliver precise carbon sequestration data, through data fusion of LiDAR and spectral images. And we're able to measure carbon by looking down to the ground and then up to the canopy to see our machine learning through our machine learning analytics. We envision Dendra becoming the platform for biodiverse carbon-rich restoration, aggregating data from sensors and networks around the world, delivering extreme transparency and enabling action-oriented decision-making and collaboration. Ultimately, we will empower everyone to achieve better outcomes and accelerate the restoration of our natural world. We invite you to consider working with us. We've built our track record on complex and challenging environments, partnering with some of the largest landowners across each nation we engage with. This transformation of workflows and environments is now being shared with more and more stakeholders globally. Without a massively scalable approach to restoring ecosystems, humanity cannot address the scope of damage to the earth. Dendra is driving Moore's law for ecosystem restoration with high quality, high trust, scalable systems. Our experience has taken us from 1,000 hectare to 10,000 hectare project scale last year, and we're aiming for our first 100,000 hectare restoration projects. We are geared for planetary scale. Join us in this journey. We're all in this together. We have many ideas we can share with governments and regulators about how to create low friction, pro scale regulatory technology investment and market friendly landscapes to win the race against climate change through natural climate solutions that deliver real biodiverse carbon outcomes. I also want to note there's some questions in the Q&A about terrain versus water, and we're obviously investing more time in terrain versus like the mermaid solutions that are out there. Although I'd love the opportunity to collaborate and build a sea drone to help get rid of a lot of the manual scuba diving that's needed for those water solutions. So just have some fun there. Thank you.
Great, thanks so much, John. So fun, effective, and cheap. That's quite a good summary of some of the work you're doing. Although you want to take the fun out of scuba diving for coral reef monitoring, I'm not sure that would go down well. Brilliant, thank you so much for that. And I'm sure there's some contact details you can put in the chat box if people want to be in touch with you to follow up on some of this. And I'd encourage all of our panelists, if you want to do so, to put your contact details and email address, something like that, in the chat box, so people can follow up. Meanwhile, let's move on, and we're going to move on to hear about how we bring together traditional ecological knowledge with emerging technologies, which is a very exciting field of development as well. Let's hear from Zoe Jewell, who's a co-founder and president of WildTrack, to hear more around this seeming juxtaposition, but I think exciting development, and how we bring together traditional and cutting-edge technologies. Zoe.
Thank you so much, Neville. I'm very excited to be here. This is co-presentation with my WildTrack co-founder, Sky Alibi. And one of the things I'm really excited about, having listened to the other participants on this panel, is the wide range of technologies available and the potential for collaboration. I think it's fantastic. So many of these new technologies actually engage other technologies, and this is one thing I'd like to focus on a little bit in our talk. So we are WildTrack. Our focus is on protecting endangered species using a mixture of kind of ancient and modern technologies. So on one hand, we have a technology which is very, very firmly founded in traditional ecological knowledge, specifically tracking, but not exclusively. And on the other hand, we're interpreting and deploying that using advanced data analytics and cutting edge technologies like artificial intelligence, which allow us to develop models that the indigenous trackers kind of see in their minds. So it's an unusual meshing of technology, but it's one that has served us well. It's been a long time in the developing, and it's been born out of our observation and training as non-experts in the field of tracking technology to be able to interpret that for modern science. So, you know, the background to this, I guess, is that, you know, we're in the middle of a biodiversity crisis. Species are going extinct at more than 10,000 times background rates. And yet, we still have, with all the technology we have, we still have country-sized gaps in our knowledge of where animals as endangered species roam and are distributed. Even with the most highly studied species like cheetah, we still have a lot of knowledge we don't have. On top of that, we don't have very up-to-date knowledge, and this is something that's been highlighted by many of the panelists. So we desperately need not only reliable data, but we need those data in as close to real time as possible. Many of the older methods of monitoring tend to provide kind of high resolution data, but they're in very small areas and they're not very easily updated. So we've developed a technique based on footprints, and you can see this wonderful image, which is actually taken by a drone in the Kalahari Desert, of a black rhino wandering across the desert, leaving a fantastic trail of footprints behind him. It's very clearly visible from the air, very clearly visible from the ground. And these footprints are really what we consider cryptic ground evidence. They are there, but most of the time, for most of us, they're being ignored. They're not being used. And yet each little footprint is a vast repository of data from which we can decode species, individuals, sex, sometimes even age class. So if I go on to the next slide, oops, too many slides. We have projects now all over the world through our Wild Track Specialist Group that are using this technology and other non-invasive technologies. And one of the beauties of footprint identification is that it does mesh in well with other approaches to give the broadest possible kind of insight into what's happening. So we work with a range of species from mountain lion, for example, in the Americas, to African lion and cheetah and rhino and white rhino in the Africas, and even to, you know, emerald tiger and leopard in Asia, and everything in between. And one of the things that's sort of evident about this to an ecologist straight away is that these are very different ecosystems. You know, the terrains are different, the climatic conditions are different. So we've had to develop a technology that is able to deliver results with a very wide range of variables, which has been a challenge. The next challenge is that every species has a different footprint, shape and size. I mean, they're all very different. If you look at this picture here, you can see, you know, the footprint of an a Bengal tiger with 4 toes and a heel is very different from a giant panda with 6 toes and 2 heels, or from a rhino with just 3 toes and a heel. And so the technique that we've developed has to be able to take into account these different footprint shapes and sizes, different substrates. Some are sandy, some are muddy, some are stony. Different climate conditions. On snow, for example, the light tends to shine very brightly, giving very poor contrast. And in other places, in dense vegetation, it's very difficult to see the footprint. So there's a lot of variation in how we've had to accommodate these variables. So what do we actually, how does the technology, footprint identification technology work? Well, it's basically a combination, as I said, of artificial intelligence mixed with the kind of gold standard morphometrics, meaning how do we understand the shape and the size of the footprint using geometry, if you like. And we've actually developed a pipeline, an AI pipeline through which the data feeds, which enables us to, we have a custom app called Wild Track AI, which takes, anybody can take images in the field using this very straightforward app. And we can then, once the images go through the pipeline, they're classified either at the species level, and then a little further down the pipeline, you can identify the sex of the individuals. And then if you get good enough quality data, and you can see this on the right with a nice clear footprint, you can start to even identify individuals and the age of those individuals. So what's kind of interesting to me about this is you can actually glean more information from a footprint often than you can by seeing the animal. And one of the great things about this, we think, is that we don't have to disturb the animals at all. We can be completely non-invasive, hands-off. And one of the advantages of that, in turn, is that the data that we're collecting, we can be confident that they're reliable. We're not impacting on the animal's behavior or its physiology by perhaps darting or tagging or chasing it. We can get the data we need remotely. And this is common now to a lot of modern technologies that we've heard about today, which is fantastic. So I think that's the kind of take home, is that we're trying to develop technology which is also able to deliver the best quality data in return. And as several people have demonstrated already today, the fact that it can be inclusive of other cultures and people who have expert knowledge in those fields is also very important. So one of the things we try to do is we try to engage, well, in fact, we do engage all over the world, we do engage indigenous communities whose expertise is, one of their major expertise is in tracking. And so these groups are often marginalized in conservation. They're not particularly included. Sometimes they're employed to help collect data, often in a fairly superficial way. But our technology actually engages them at a very deep level. So we rely on them in the field to help us find and identify the best places to collect data. We rely on them to help us interpret the data. We're relying on them to help us strengthen our algorithms to find out which variables they're seeing in the data that we're not. So they're very, very much engaged. And I believe they're hugely underrepresented in helping move towards the SDG targets. So our vision really is to have these groups all over the world, whether they be indigenous Inuit people through to people, sand groups in Southern Africa. And here you can see a grandfather, his son, and the father to his grandson, all out looking for footprints together. These guys are teaching the little guy how to track, and the little guy is showing them how to use the modern technology, the camera. And now we actually have an app as well that can use it. So it's a fantastic tool to allow us to collect data through their expertise, but also for them to kind of keep that traditional ecological knowledge alive. Because in many parts of the world, it's disappearing. It's not valued, it's not valued because it's not being used. So I think all of us here probably are in agreement with that. We're speaking to the converted, but I think it's something that conservation in general can learn a lot more from if we kind of listen to these people. And what we're using with footprints really is just a tiny fraction of their traditional ecological knowledge. There are many, many other areas to start looking at decoding and exploring for global benefit. So I think to sum up where we are with this, we have a technology which is data-driven conservation. We want to be able to populate the world map in the way that we've seen some of these other wonderful technologies doing, and provide kind of real-time insight into where endangered species are and how many there are and where they're going and what they're doing. And all these things that we need to be able to develop effective terrestrial conservation strategies. We feel we have a technique which is very community inclusive. It's based on indigenous tracking skills, which allows us to widen the field of participation enormously. Even within non-indigenous groups, there are something like 8 billion visits to protected areas every year. And if we could even harness a fraction of those people to collect data on their phones every time they see a footprint, we would have a vast amount of data, far more than we would ever get from people, conservationists like us going out into the field into selected areas on a specific field trip. What else? So technology is non-invasive to the animals. There's no negative impact of hands-on. And that is something that kind of feeds into something very topical, which is there's much less risk of something like COVID or other disease transmission from animals to humans. We don't have to handle them or get close to them. And I think there's huge potential also for the kind of more applied areas here rather than just pure science, which is environmental surveys, impact assessments, human-wildlife conflict, looking at anti-poaching strategies. I think the potential is huge. These little footprints are all over the world, and once we know how to decode them, they can be a very powerful tool in combination with all these other tools that we have for protecting our rapidly disappearing biodiversity.
Wonderful. Zoe, thank you so much indeed for that. And I'm conscious of time, so sorry to help to move us on. I'm going to call all of the panelists' attention to the excellent question we've had from Suzanne Macy in the chat box there, sorry, in the question and answer box. And thank you, Talia, for your response to that. I'll encourage other panelists to pick up on this too. In relation to the ethical and surveillance concerns for local communities, Indigenous communities that come alongside the increased use of technology sensors. So a really important question and some concerns that Talia is recognising need to be further addressed. So maybe Zoe will have a chance to pick up on some aspects there as well, given the closeness of your work with a range of local communities. That would be fantastic. Meanwhile, let's move on to our last panellist. And we're going to hear from Devaya Ayama, who, depending on which piece of paper I look at, is either the conservation manager or the community manager for the IUCN Green List of Protected and Conserved Areas. So maybe, Devaya, you can confirm what your title is and then tell us more about Tech for Nature. Thank you.
Sure, Neville. Thanks very much. Thank you to the organizers for the invitation. I can confirm that I'm both. I'm involved with the community facilitation of the IUCN Green List as well as conservation project manager for projects related to the Green List, and that was my first introduction statement. So by way of introduction, I'm also based out of IUCN's Global Protected and Conserved Areas team here in Switzerland, based out of IUCN headquarters. I'm a conservation biologist by background, so not a technology specialist, but very interested in the appropriate use of technology for more efficient and greater conservation impact. So it's encouraging to hear from Talia that everyone in this space has an important role to play. So excited to be here and great to hear from all of the inspiring speakers. At IUCN, I work on the IUCN Green List, as I mentioned, of protected and conserved areas. The Green List is the first global standard of good practice for effective and equitable area-based conservation. It's a voluntary program of certification for protected and conserved areas that are fairly governed and successfully delivering on their conservation outcomes. But today I'm providing a quick summary of one of the projects that I manage, very relevant to this event, called Technology for Nature, or Tech for Nature for short. It's a relatively new project, fully kicking off really at the beginning of last year in 2021. And Tech for Nature starts off as a global partnership between IUCN and an ICT sector global company, Huawei, with the vision of scaling up success in nature conservation through digital technology innovation. Created specifically as a partnership between the IUCN Green List and Huawei's Tech for All program, which is the company's digital inclusion for sustainable development program. Tech for Nature is designed as a partnership between bringing the conservation and ICT sectors together to apply and promote digital technology solutions to advance fair and effective protected areas for enhanced conservation impact. So it is about harnessing innovative technologies in support for better conservation outcomes in and around protected and conserved areas globally. And that conservation impact is assessed through the use of the IUCN Green List standard. The global project provides guidance on the appropriate use of technology in the protected area context, so specifically in area-based conservation by following the IUCN Green List standard, and the project directly involves the ICT industry sector. As a new project, some key steps, just to give you an idea of how we go about identifying. It's a global project, but we have projects in about 5 flagship countries and additional countries as well. I'll just give you a quick idea of some of what's happening in the 5 flagship countries. Starting with, just to also note that we're in fairly early stages of these pilots. So we've spent a good part of last year setting up these projects. And we're just in the initial stages of getting some initial results. So I won't be speaking so much about results, but just give you an idea of these 5 flagships. In Switzerland, we're testing a blockchain-based carbon sequestration methodology that's aligned with the IUCN Green List standard in a managed forest reserve. The key partners in the Switzerland project are Peña Foundation. It's a small Swiss nonprofit with a mission of advancing conservation technology for impact. The forest reserve that's set aside by a forestry company, and Huawei Switzerland, who's providing the blockchain technology solutions. In Spain, we're working with St. Lawrence National Park near Barcelona to co-design a technology-based monitoring solution for threatened bird species in the park that's easily disturbed by tourist visitation near its nesting sites, which can potentially have significant negative impact on its fitness. So through camera trap technology and electronic fence monitoring, the project aims to provide improved monitoring of the nesting behavior of the species, as well as tourism impacts and risks from visitation to the nests in the park. The key partners besides IUCN are the Parks Authority, a university that's helping with some of the monitoring methodology, and Huawei Spain as the technology solution provider, along with some suppliers of Huawei, tech suppliers of Huawei. In China, we're compiling over 100,000 digital acoustic records via a set of networked acoustic sensors for designing an AI machine learning auto recognition algorithm that will help greatly increase the efficiency of species monitoring to support the conservation of a critically endangered primate species, the Hainan gibbon, in the Hainan Tropical Rainforest National Park. Key partners there are, of course, the park, as well as its research institute, along with an algorithm design partner and Huawei's China office. In Mauritius, we're prototyping one of the first underwater real-time digital cameras in the Western Indian Ocean region to support monitoring of active coral reef restoration in a locally managed marine area, with benefits planned for both biodiversity as well as fisher communities. Key partners there include a local conservation NGO doing the reef restoration, Huawei Mauritius, as well as Mauritius Telecom, another ICT company that's interested in conservation impact, who are providing the technology solution design and implementation. And last but not least, the fifth flagship country is in Mexico, where we are deploying and collecting data from camera traps and acoustic monitoring devices with some network connectivity, powered by some AI and machine learning analysis to improve ecosystem and key species monitoring in a protected area, which is also a Ramsar site in the coastal zone of Yucatan. Some key partners there include the State Parks Authority, as well as a local nonprofit, a nonprofit working at the interface of technology and sustainable development impact, as well as a local university who's helping with AI and machine learning analysis, as well as technology partners from Huawei Mexico. So that's a very quick global overview, and in the interest of time, I'm going to close just with some key learnings that I thought would be relevant to share here that we've seen through the implementation of this new and innovative project. So we're still learning, and the project is, I'd say, in its midpoint, so there'll be more learnings and more results to come. The project will run till the end of 2023. Firstly, I think that partnerships and innovative ideas are key to this kind of a project. The bringing conservation partners that bring the detailed understanding of the conservation challenge and what's needed to address it, and having tech partners that bring the detailed understanding of the technology, and just bringing these two sectors together generates a lot of new innovative ideas. The second point is that it can take some time, though, when you're bringing two different sectors together to understand a common language. As I think Neville was mentioning earlier, there can be a lot of techie terms and acronyms, and similar both in the tech world and in the conservation world. So I think it can take time to understand the two perspectives, but it's definitely worth taking that time so that it can only result in really well-designed, co-designed solutions that really are realizing that potential of technology to address that specific conservation challenge. It can also be recognized that it can also be expensive. Technology, depending on the level of sophistication of that technology, can be expensive, but we're also seeing that the cost of technology is decreasing in some cases. So high-end camera traps are much more reasonably priced now than they were 5-10 years ago. So they're becoming more accessible. So just by providing a bit of seed funding to provide a set of 5 network camera traps can make a huge difference to a protected area that's interested in technology, but just didn't have that little seed fund to demonstrate and use its impact. And finally, I think the last point that we'd like to emphasize in the context of Tech for Nature is that technology is not a silver bullet solution to a conservation challenge. So in the context of this project, the IUCN Green List standard really ensures that implementation is done following good conservation and good governance practices as defined by IUCN best practice guidelines and by the IUCN Green List standard, so that technology solutions are deployed appropriately and inclusively in the context of a systematic conservation plan with clear goals for fair, inclusive, and long-term conservation success. With that, thanks very much again to the organizers, and thanks to my global to local team members around the world who, of course, are implementing this project. Thanks.
Wonderful, Devaya, thank you so much indeed. Very interesting to hear about that. Yes, to confirm there were no slides that people missed for that presentation. That's a
yes,
great,
no slides.
Thank you for that. Now, we've heard about the application of technologies at various scales, local communities, the watershed scale for eDNA. We had a great example of the drone mapping the cliff face. We've heard from Devaya about the application in particular protected areas. We heard from Zoe about the application in footprint scales, exceedingly local scales on the ground. Let's hear a bit from the national level. We're lucky to be joined today by the Deputy Permanent Representative from Gabon to the UN, who is going to share with us just a couple of minutes on the application of conservation technologies at the national scale in Gabon. So Aurelie, I think we have you online and you're good to go.
Yeah, thank you very much. And first of all, do you hear me?
We hear you well, but we don't see you.
Okay, I do not have the possibility to open my camera, so you just have to hear me.
Sorry, we cannot do that apparently. So just go ahead, please, Madame.
Okay, thank you very much. I want to congratulate the panelists for the presentation. It was very clear and useful. And I want to say that I want to share the Gabonese experience in applying modern technology solutions to get a reliable estimation of wildlife population. So under EU funds,
I think sadly we've lost Aurelie. That may be a connection issue. It may be that she's no longer in the panelist list. Anyway, let's see if, she's back.
Okay, I'm back. Sorry.
You're back, yeah.
Okay, sorry for that. I want to share the experience of Gabon in application of modern technology solution to get a reliable estimation of wildlife population. So under EU funds, INPN, which is the national agency in charge of the management of protected areas, the network of protected area, and its partner, we developed a new artificial intelligence algorithm for automatically detecting the Central African forest mammals in camera trap image. And this algorithm named Mbaza AI is used to build an easy to use free camera trap data analysis platform. And you can use it on any standard Windows laptop without access to the internet. And you can analyze up to 2,000 images per hour. The software is available in both English and French, and we are adding new models so that Mbaza can be used in other parts of Africa. The algorithm has accuracy up to 95% for several species and can even detect animals in images that cannot be seen by humans, such as camouflage birds. And to date, the software has been used to analyze more than 500,000, I don't know, images, but from protected areas and forestry concessions in Gabon. Okay, and building on the success of this algorithm, there is also, we are working to build camera traps with built-in artificial intelligence algorithms that can provide real-time data from anywhere in the world. And this camera analyzes captured images and detected species it's sent as a summarized text alert over satellite network within minutes. So I can send you these are being published. Banza AE is already published, and for the use of the smart cameras, there is a preprint, but I can send you the DOI. We also, by now, there is a 5-year funded project named FODEX, standing for Tropical Forest Degradation Experiment, which is carried on field in order to design and to test methods of mapping tropical biomass change. So there is a large forest plots in logging concession in Gabon that are set up, and then all trees within these plots are measured and scanned with laser scan and LIDAR. Then the plots will be locked with a proportion of trees removed ranging from 20% to 80%. And then the plot will be remeasured, will be scanned. The plots will be tracked over the following years of recovered with scanning of and measuring of trees twice more. So that is a summary of our experience using new technology for conservation. Thank you. And sorry for my English and my
No, that's wonderful to hear. Thank you so much indeed. And you were mentioning the number of images you'd used and scanned there. It was 500,000 you were mentioning. Yeah. So that's a huge number that's been processed. Great to hear.
It's a great solution.
Great to hear. Thank you so much indeed. The application, very practical application then. Thank you for the link you put, I think just into the chat box to host and panelists, but we'll make sure that everyone has a chance to see that when in the next step. Thank you so much for that. I'm very conscious of time. We don't have a huge amount of time for additional questions, but thank you to all of you who have asked questions, and almost all of which have now been responded to in the question and answer box. So thank you for that. Of course, we've not had a chance today to cover all conservation technologies. So if you're interested, for example, in blockchain, then you need to go back into the Q&A box and look at the responses coming in on blockchain. We've not had a chance to look at some of the LiDAR technologies, many other technologies out there, which are being scaled up in use and deployment. But what we have done today is have a chance to look at how various conservation technologies have developed and are being applied at various scales for conservation gain on the ground in the ocean to ensure they are put to work for conservation benefit. And that is, of course, what is going to be important as we continue this journey to deploy and apply conservation technologies, that they are used in practice. They are scaled up in their use. And as we heard right back at the start with Talia before the panel presentations, the more conservation technologies are used, the more they are useful. We heard that as well from Emily in relation to the Coral Reef mermaid work as well. So we need to be using these technologies for the price to come down, for the data to be built up, for the accessibility to increase. And we have to overcome those challenges that Talia brought to us at the beginning on equity of use and uptake of technologies. I will encourage you all as you go from this session today to think about two key things. Firstly, how can we continue to overcome those barriers so that all parts of the planet can benefit and all people can benefit from conservation technologies to enhance the conservation of life on Earth, to make progress towards SDG 14, SDG 15, many other SDGs, we heard from Hal as well, are relevant for these conservation technologies. And so we can apply these to success for delivering on the post-2020 global biodiversity framework, the ambitions of that framework. Conservation technologies will have a huge role to play, but as many of the panelists have said, they are not the only solution. They're part of a wider toolbox we need to deploy for success. And then my second question is this: given the potential to have impact from conservation technologies, given the importance of us all having a role to play, what are you going to do to scale up the use of conservation technologies off the back of this very important and very interesting and very informative discussion that we've had today in the margins of the high-level political forum. What commitment are you taking to further the deployment, further the use, further the equitable access to conservation technologies for the future? And with that, I would like to pay a huge thanks to all of our speakers and panelists today. A huge thanks to all of you who've been joining as participants, your questions, your engagement, your chat contributions, and a huge thanks to the Permanent Mission of France, to the UN, to IUCN, and to WCS for convening us and bringing us together for this very important, very interesting discussion today, and look forward to lots of follow-up. Let me just see, David, am I handing back to you at this point?
Yes, to say, and a huge thanks for the moderator, Neville Ash, who did a brilliant job. And so thanks all. We will be sending out a link to the recording within 24 hours for all of those who have joined, who want to listen to all these fantastic presentations again, or for those who couldn't make it, who registered but couldn't make it. But we did have a large crowd at the peak, about 135 people. So that's a very encouraging audience. And thanks to the audience as well. And look forward to future knowledge dialogues of our three partners. Thank you again. And have a good rest of the day, rest of the evening, rest of the HLPF. Bye-bye, everyone. Thank you.